second part I'll build is the oscillator, which is Q1, and all this stuff, sort of, all that stuff there is the oscillator. Just a standard Colpitts oscillator, R1 sets the bias for the transistor. The feedback capacitor is the crystal. This D2 here, you'll notice, is reverse biased, and that's because diodes exhibit some capacitance when they're reverse biased. And so when it's in series like that, it will pull the crystal frequency up a little bit. And then on key down, when this key line goes to ground, it'll ground all this stuff and change the reverse bias voltage across this diode, which will change the frequency. And that's how we get the transmit receive shift. You can adjust the little trimmer potentiometer here to change the amount of shift that you get. So we'll build that and see how it works. So D2 is used to provide a little bit of capacitance to change the transmit receive offset. And as you can see here, I pulled up the data sheet for the 1 in 4001 transistor, and apparently the stats are similar for all these other ones. But if we scroll down through it, under electrical characteristics here, we can see the typical junction capacitance is about 15 picofarads. But if we keep scrolling even more, this chart here in the top right shows you the junction capacitance as a function of the reverse voltage. And so ours, the maximum reverse voltage will be about 7 or 8 volts. So if you look at the line, that means we'll have, you know, a little over 10 picofarads. Then as the reverse voltage goes down, that goes up. Here's, you know, 10, 12, maybe even a little more than 12 picofarads. So that's the sort of, if you want to replace the diode with just a capacitor to switch in and out, you probably need one around 10 picofarads to get a similar sort of transmit receive offset. Now that we've built the local oscillator, the LO, which is the stuff around Q1, we can test it out. So I've got the scope probe hooked up to the output of the LO on C4, and this is just a straight key I have plugged in, so we can see that the transmit receive offset works. And so I will look at the scope. When I plug this in, we should see, look at that, it's more or less a sine wave. I don't know if you can read that frequency. It says 7.03, 7.02. It's flickering around there. We're getting about 2.1 volts RMS out of this stage. I'm not sure that we have enough, that the scope is good enough that we'll see a difference in frequency when I key down. It looks like the waveform just gets a little bigger, but it's not registering any frequency change. But there's another way we can listen for frequency change. We'll just use the big rig. So here's the KX3. I got this wire on a BNC to binding post just to help pick up the oscillator a little bit. So that's on. So if we tune around, this is the crystal frequency. Because of the diode and series and other stuff, you're usually not right on the frequency, but yeah, here we go. There's a very strong tone. About, yeah, 7.023.52, which, yeah, it's not bad. And then if we want to adjust it on receive, we can just spin this. So if I do that and you listen, you can hear the tone is out of the passband. If we tune down, we can find it again. And I think I can go a little farther. Yeah, that's the other end of the range. 7.022.96. So if I had a piece of paper, here's a piece of paper, we can write these down and figure out what sort of transit receive offset we're capable of getting. So at the low end, we have 7.022.96. And if we spin this all the way the other way, and tune back up, we're at about 023.52. And so I wrote those backwards, but 96 to 52 is 580, 0.580 kilohertz. So 580 hertz is the maximum transmit receive offset we'll be able to get. So I think I'll leave it and leave the potentiometer here spun all the way around, because I like to listen to like a 600 or 700 hertz tone. And if we key down, it just goes away. But if I tune down to, what was it, 22.96, somewhere around here, and I key down, so a little bit chirpy there. But it's working.